so you reject. If you have large p-value, you do not reject. Okay? So when I say reject and not reject, I'm talking about the null hypothesis, basically. All right? Okay, so if you reject the null hypothesis, that means you accept the alternative. Okay? If you do not reject the null, that means you reject the alternative hypothesis, because I could not reject the null, so I accepted the null. Accepting the null hypothesis means rejecting actually the other hypothesis. Okay? So that's the decision rule here. That's what you need to keep in mind. So p-value, small p-value, reject the null. Large p-value, you do not reject the null. Okay? Any questions? Yes?
So if it's equal, then do you reject the null?
That's the marginal case. That's what we took. So it could go either way. So it depends on how you're gonna interpret it. So you can say I reject because this is very close, or I can say accept because it's still very close. So that's why we say it could go either way. So that's the case we said here, that if the p-values are very close to alpha, it is considered to be marginal, because the reason here is it could go either way. You can accept or reject in that case. Okay? But let's say if it's very close to 5%, that means this is like a marginal case with 5%, but if you change the alpha to 1%, you want to be more sure or more confident, so that means it's greater than 1%. It's almost 5%, so if it is almost 5%, so 5% is greater than 1%. Okay? And in that case, you have a large p-value, which means you cannot reject the null hypothesis. Anyway, but if you want to make the decision based on 5% significance level, and in that case you get p-value that's very close to that 5% or even equal 5% exactly, so that's the point. This could be considered as marginal, so you can reject or accept, depends on the context what you're doing, but you need to explain that is because it's marginal, because it's very close to the alpha. That means it could go either way, and you need to explain this a little bit more. Okay, so the question now, is it possible for us to make a mistake? Yes, of course. So the mistake here is that I reject the null hypothesis while it is true. Okay? Or and what I've said now, we call it type 1 error. So the null hypothesis is correct, but actually I reject it. So the decision I made is I rejected the null while it was true. Okay? And alpha here is the probability of making type 1 error. So, which means the probability that you're gonna reject the null while it is correct. Okay? Type 2 error here, if you reject the alternative while it is true. So rejecting the alternative means that you accept the null. When I reject H1, that means I accepted the null. Okay? While H1 is correct, I shouldn't reject it. Okay? That's what we call type 2 error. So that's the probability that we may make a mistake when we decide to accept, to reject, or to accept the, or to be more accurate, I would say to reject or to not reject the null hypothesis. Okay, any questions? Because what we're gonna do next now, we're gonna have some example. We're gonna do this in SPSS. So I'm gonna use the software. So if you, before we go to the examples, I would like to summarize the whole story, sum up the whole story again. So the whole story now, we have a population. We want to know, or we want to test that the mean of that population equals some constant, some figure, some number, the example that we gave is the weekly working hours in the UK. We say, in that case, we want to test, or we want to ask whether people in the UK work 35 hours per week. So based on that question, it comes the population. So that's how we identify the population. How we identify the population is based on the question we ask it. So the population in this case is every single person, working person in the UK. Because it is difficult, all what I have so far is the hypothesis, is the question that the mu, or the mean, or the average working hours is 35. That's something in my mind. That's the question about that population, which I can't ask every single working person in the UK how many hours they work. The only thing I can do is to draw a sample. Once I draw a sample, just giving that we understand that this sample should represent the whole population. Once I draw a sample, I have observation. I see something now. I can easily calculate the mean of that sample, which we called x bar. So I have mu, which equal a constant, which is 35, the one that I'm trying to test, against the sample mean, which is whatever you calculated. So we apply the t-test, we get the value for the p-value, and now, first of all, sorry, I should say this in the same, like more accurately. So I need to look at what the null hypothesis is first. So the null hypothesis in that case, that mu equal 35. The alternative could be that mu does not equal 35, and in that case, based on that alternative, I have two-tailed test. Or you can say the null is that people work more, on average, work more than 35, which means that mu greater than 35, that would be one-tailed test. Or people work less than 35 hours, so that means mu less than 35, which is, again, means that we have one-tailed test. So whatever you choose here, so let's say the first thing is the null hypothesis and the alternative. Then I decide on the significance level. Let's say it's 5%, the most popular one, and which means if I choose significance level 5%, that means I'm 95% confident about the decision I'm making here. Then I calculate the t statistic, which is the x bar, the mean that I got from the sample mean, minus the one I'm hypothesizing, or the one that I'm assuming is like the 35, the one that I'm questioning here. So x bar minus mu, that's over the standard deviation of that comes from the sample. Again, this is something that I can observe because it's based on the sample, so I can calculate easily. And we learned how to calculate the standard deviation before. That's divided by the square root of n. N is the number of observation. Let's say I got the t-statistics and I got the associated p-value. P-value here, so I have two values. I have the p-value, I compare between the p-value and the alpha, the significance level. The alpha we decided on, and we said it's 5%, and I told you this is something arbitrary before, so let's assume that's 5%, that's fine. So, and we understand what 5% means, that I'm 95% confident about what I'm saying now. So that's 5% is the alpha, again it's the p-value. So if the p-value, how to make the decision, how to take the decision now, if the p-value is very small, which means relatively small, which when I say small, that means when you compare it with alpha, with the significance level. So if it is very small, so that means you reject the null hypothesis. If I reject the null hypothesis, that means people in the UK do not work on average 35 hours, because that was my null hypothesis. That mu, people on average work 35 hours. So rejecting that null means that people do not work 35 hours. Okay? If the p-value is large, is greater than alpha, that means you cannot reject the null, which means you accepted the null, which means again that yes, people work on average 35 hours. Okay? We talk about the two types of errors, that how likely we might commit a mistake or make some mistake. It's when we reject the null while it is correct, that's mean type 1 error. when we reject the alternative while it is correct, that's type 2 error. So that's pretty much everything we say today. So let's move to some examples. So that's the example that we had last week. We have the production line filling bottles operates somehow, and we assume that it's a normal variable. The system aims to fill bottles with 1,000 ml, and we get a random sample. Again, assuming that this random sample means that the way we pick that sample from the population, it represents the whole population. Okay, so the sample that we draw here has 6 observations. 1, 2, 3, 4, 5, 6. Yes, 6 observations. And now the question is the difference between the hypothesized population mean, which is 1,000, and the observed sample mean is statistically significant at 5% levels. So the difference, if you remember from last week's example, we calculated the sample mean, and it was 1,010, and I started with this lecture. I show it to you. Okay, so and we're gonna have it now again in SPSS. So the idea is that the sample mean, the X bar here is 1,010. The hypothesized one, or the one that comes from the population, which is mu in that formula, is 1,000. So I'm asking the question now whether this difference is really statistically significant. Is it something huge that I should consider, or I should say, now there's something wrong with the current system, and we need to check this system again until we achieve, in order to achieve this target or not. So now the first step here is to decide the null and the alternative. So the null hypothesis is that the mean value, or the mean, the population mean, which is 1,000 here, mu equal 1,000. So that's what I'm trying to test here. Okay. The alternative, that mu does not equal 1,000. Okay. So again, if mu equal 1,000, if I accept that null, that means the current system is fine. We don't need to look at this again. Okay. Do you remember, based on the confidence interval, the decision that we made last week was that we need to reconsider that? I'll show you this. Because we have the lecture here. When we let's see. So if you look at this one, I'm not sure if you can see this or not, but here, let me zoom in a little bit so you can see the table. So when we look at the 90% confidence interval, we found that the lower bound is 1,000 point something, and the upper bound is 1,019. And what we were trying to see is the mean from the population, which is 1,000, lie between these 2 points. And because it is not between these 2 points, that's the conclusion we made, that this system might need to be checked again. Okay, so now we're doing the same thing, but in a different way. Now we're doing this by doing this hypothesis testing based on the significance level. So our question here is that whether mu equal, which mu here again is the population mean, equal 1,000, against the alternative hypothesis that mu does not equal 1,000. In that case, we understand that we have two-tailed test, because once I say that mu does not equal 1,000, could be greater than 1,000 or less than 1,000. Okay, so I'm looking at two sides, this side and this side. So that's why we say we have two-tailed test. Okay, so again, the next step is to decide on alpha. So given that, okay, we can assume that alpha is 5%, and then we need to calculate the t. But let's do this. Okay, to calculate the t, just let me remind you the formula, which SPS does for us. So the next step is to calculate this t statistic. Now we have x bar is 1010. You remember? X bar, the one comes from the sample here. So that's sample statistics. So that one that we calculated last week, which is 1010. So X bar here is 1010. Mu minus mu is 1000. The hypothesized value for the population mean. Okay. So let's do this in SPSS, see how to do it, and then we'll see how to make a decision. So let's go to SPSS. I have it open here. Let me enter the values. So now we have a sample, and this sample has 6 observations, which is what 1019. Okay. 1019 and 998 1029 and then two. So the way we do this in SPSS, we need to go to Analyze. So you need first to enter the data into SPSS, and then you go to Analyze, and from Analyze you go to Compare Means, which is here, and then one sample t-test here. So we enter the data, go to Analyze, Compare Means, one sample t-test. Okay. I think I entered the data wrong way, sorry. If I do Analyze, it's variable 1. Yeah, so I choose the variable they want to run the test for, and then we want to test, that's the value we want to test for, so that's the population mean. Okay, so we want to test whether this equal 1000, mu equal 1000. Okay, and if we choose from options here, we can choose the confidence interval. So if this 95% means the significance level is 5%, and that's our task. That's what we are supposed to do. We want to do this test based on 5% significance level. Okay, so that's why I write here 95. 95 means that alpha equals 5%, 0.05, okay? And then we click continue. So again, then the last thing I would say, I would press OK. But just again, so we went Analyze, Compare Means, one sample t-test, and then we choose the variable that we want to test, and then this is the mu. That's the value I want to test, and from options I go to choose the significance level or the confidence interval, which is the complement to the significance level. So if I want to choose 5% significance level, I type 95% confidence interval, and then we say OK. So now what we have here. This part explain what we're testing mu equal 1000. That's the name of the variable. Just call it, like, give it any name. And this is based on 95% confidence interval, which means 5% significance level. All right. So again, it calculated the sample mean, which is x bar, okay, which is 1010, because it's the same example from the previous week, so it's the same number here. So we have the same sample. The number of observations is n is 6. Now it comes to the point that we need to make a decision here. So what we need to look at, calculate the t-statistic. It's this one. Do you know how to calculate the t-statistic? Do you remember formula? The formula is x bar minus mu over the standard deviation over divided by the square root of n. So now SPSS give you this straight away. So that's the t-statistic, and the associated significance, p-value is this one. So now we have p-value of 0.093, which is, to make a decision now, you need to compare this one with alpha. So the alpha was 5% because we typed 95 in the cell for the confidence interval cell. We typed 95. 95 means the alpha 5%. So when you look at this now, 5% is 0.05. So this one you have large p value. This one is greater than u alpha, which means you cannot reject. Okay? So if this one is small, so you reject. If the p-value is smaller than alpha, you reject. But because it's not smaller, it's greater than alpha now. It's large p-value. It's 0.09, which is definitely greater than 0.05. So that's why we say we cannot reject. Okay?